Hello friends, and welcome to another example video for electromagnetic induction in A2 physics. In this video, we are going to look at induced EMF between two coils. So let's go. Question is from Winter 16, paper 41. So it goes like this. Of course, they're going to get you some question to warm up first, which is a definition question. So you are asked to state Faraday's law of electromagnetic induction. Okay, so this is 2 points. Make sure that you mention that this is an induced EMF. So the induced EMF in a closed circuit or a closed loop or a conductor is directly proportional. Don't use the word equal, use the word directly proportional to the rate of change of magnetic flux linkage. So this is a bonus. So the 2 marks is given to you provided you learn how to write the actual definition properly. Okay, moving on. The diameter of the cross section of a long solenoid is 3.2. So if you are a bit the type where you notice that sometimes, hey, there's a possibility that I may make a mistake, I'm going to immediately write radius as 1.6 cm here. Okay? Because I know I have to find area somewhere along the line. The coil C with 85 turn of wires, so your N is here, is wound tightly around the center region of the solenoid. Alright, let's look and try to brain this drawing first. You see here, there's a coil C. I'm going to highlight coil C. This is your coil C. Okay, it's tightly wound and it's wound around the solenoid. Which is the solenoid you asked? The solenoid is this coil. So the one with this current, this is the solenoid current. Okay, blah, blah, blah. TLDR. So this is the solenoid. Okay. Where's the current in the coil? I don't know. Read the question first now. The magnetic flux density, B in Tesla, so this is B in Tesla, at the center of the solenoid. And this coil C is right at the center. I mean, it looks at the center to me. Center region. So this is the value of B. B is right in the middle here. And this value of B is equal to pi times 10 to the power negative 3 times I. Well, if they give you an equation, say thank you and use it. Thanks, A-levels. Where I is the current in the solenoid in ampere. If you want to know a bit more about the equation, you can always go to the first video of chapter 22. Alright, if not, just use the equation, which kind of makes sense anyway, because from here I can see that the magnetic flux density is proportional to current. Larger current, greater magnetic field. Good. Show that for the current of 2.8 ampere in a solenoid, so this is I, the magnetic flux linkage is equal to 6.0 times 10 to the power negative 4 Weber. Okay, many information. We're going to start with what they want first. They want from us the magnetic flux linkage, which in this case is NBA, National Basketball Association. Alright, and you look at the linking, this is obviously 90 degree because they are overlapping on top of each other this way. So the area is 90 degree. Very good. Okay, so we're going to put in N. N is our beautiful 85. What is B, miss? There we got B already. What? Pi times 10 to the power of negative 3 times I. Okay? And the area here will be pi r square. Area of the solenoid. Okay? They wrap around the same coil. I think it is safe to assume that because it is wound tightly, both solenoid and coil is approximately the same radius, more or less same value of R. Okay, so I can use back 1.6 cm. So this one, I will substitute now, 85 pi 10 to the negative 3. Value of current is 2.8. Okay, another pi here. Radius is 1.6 times 10 to the power of negative 2. cm need to convert to meter so that the final answer is in SI unit. So now we can press our calculators. Okay, and if you do so, you will get the answer of 6.01 times 10 to the power of negative 4, which is approximately 6.0 times 10 to the power of negative 4. Beautiful. Current in the solenoid is reversed in 0.30 seconds. Calculate the average or mean EMF induced in coil C. Something that you should really pay attention to is the word reversed. Okay, so if we reverse the current, it means that the flux, the change in flux goes from, let's say, positive 6.01 or 6.0 times 10 to the power of negative 4 to 0 to negative 6.0 times 10 to the power of negative 4. So when we reverse, okay, when we change the direction of the current, we flip the direction of your magnetic flux density, meaning we will change the positive and negative sign of your flux, right? So your flux is not 6.0 become to 0. It is 6.0 to 0 to negative 6.0. So if you want to find the mean EMF, this E, and when you apply your Faraday equal to d flux dt, please be aware that this change in flux is not 6.0 times 10 to the power of negative 4. This is merely the amount of flux. It is not the amount of flux that causes an EMF. It is the fact that your flux is changing that causes the EMF. So when your flux change, you have EMF. And the flux didn't drop from 6.0 to 0. It dropped from 6.0 to 0 to negative 6.0. So can I just times 2? Can I? Because of this. Alright. Or minus negative 6.0, then times 2. Alright, so I'm going to divide this by how long is it? 0.3 seconds. So if I press my calculator, this will give me the answer of 4.0 times 10 to the power of negative 3. Thankfully, this is already, wait, I am blocking the sign. My bad. This is already millivolt, so you can write this as 4.0 millivolt. Always check the unit, okay? Don't simply just hantam and put the negative 3 there. Okay, so in case the future me is a lost human being, sometimes it happens to the best of us, I will write the times 2 here to show that it is a reversed, your current is reversed. Okay, so this is how you make notes for yourself when you do revision and later day you go like, oh, better don't make the same mistake again. I could see this happening to me if I didn't take care about the word reverse. All right, so let's move on. Ooh, graph. I love graphs. Not sure about you. Okay, so this is the current in the solenoid, and it is varied with time as shown in figure 9.2. So you can see this current, or it starts with 2.8 constant, and then at this weird timing, neither here nor there, I guess this one, this value here is 0.3 lah. Okay, 0.3. Just like this value here is 0.6, and this value here is 1.0. So you can see from 0.3 to 0.6, the value of current has dropped. But you see the current reverse direction. This is negative 2.8. And if I look at the time it took for it to reverse, the time happened to be the same amount of time we calculated just now, 0.3 seconds. Okay? And then if you see here, this one is 1.0. But what is this? This is 1.6. So the current still reversed from negative 2.8 to positive 2.8, but it took double the time. So from here to here, it will be 0.6 seconds. Okay, so it took double the time. So use your answer in C. My answer in C was the induced EMF E is 4.0 millivolt. Okay, this is my answer in C. Just going to draw a circle here. To show that in figure 9.3, which is this graph below, the variation of time t, so how does your EMF induce changes with time in coil C? 4 marks, ladies and gentlemen. It is 4 marks. So if I were you, I'm like, I must show all the important values, the x-axis, the y-axis. I must draw a beautiful graph to get 4 marks. All right, so first things first. I draw what I confirm know, which is the places where I know that there's no EMF. So where is there no EMF induced at all? Be here, lor, because current is constant. Here, lor, current is constant. Here, lor, current is constant. So I'm going to draw a label here for your notes. I'll say that in this color, the EMF is 0. Why? Because I constant. Hiya. So I'm going to draw this part first lah. Easy mark. We say thank you and tick first, okay? So 0 to 0.3, which is the middle here, this will be no current. Okay? Then 0.6 to 1.0, also no current. And where else no current already? 1.6 onwards, also no current. Well, guys, during the exam, you better make sure the line that you draw is slightly thicker than the axis, okay? So black also can see. Because you're using a pencil, and your pencil will be black. They will scan your pencil, scanner is black. So draw it a little bit thicker, so it's really clear that it's 0. All right, and we know the value for this one, right? Because from here to here, okay, let me scroll up a bit. From here to here, this portion, let me highlight this for you. So for this one, the current of 2.8 ampere is reversed in 0.3 seconds. So this is the same as this calculation that we did previously. Miss, where got 2.8 ampere? Nah, the 2.8 ampere came from here, ma. So this 2.8 ampere is reversed. So when the current is reversed, the flux is also reversed. Also reversed. Okay, that's the only reason why your flux changed. Your flux didn't change because your area changed. Your flux didn't change because your number of turn changed. Your flux didn't change because it is moving in a non-uniform magnetic field. The only reason why your flux changes is because the current inside the solenoid changes, which changes how strong the magnetic flux density is, which then changes the flux. Okay, so in this case, your I is reversed from 2.8 to negative 2.8 in the same period of time. So this is 4 millivolt. So I'm gonna right here. So hence for this one, the induced EMF is 4 millivolt. So I'm gonna draw 4 here. I guess if you want to, you could just draw 4 boxes lah, because I kind of don't know what the other one is. But if you have the foresight, you can actually tell that this one is, it took twice the time. So if it took twice the time, then the rate is half. If the rate is half, the EMF is half. So this part here, heck, we reverse the current. So for this one, this I is reversed. Same I, still 2.8 to negative 2.8, but this one is in double the time, 0.6 seconds. So the EMF will be half because the change is slower. Yeah, just like life law, if the change very fast, then you have to create large EMF to oppose that change. But if the change is slower, your resistance or your reluctance to change will be smaller. Okay, so it reflects in a smaller EMF. Or I guess if you want, since you already calculated the value of 4, you can actually go back here and stare at this number. The current is still 2.8, so nothing on top has changed. This 0.3 becomes 0.6. So if the 0.3 becomes 0.6, this will become 2.0. Alright, so meaning I will have a 2.0. So the scale I could use could be, I guess I could use a scale of 2. This is already millivolt, which is beautiful. 1, 2, 3, 2, 4, 5. Okay, so this is 4. And you might be thinking, do we need to flip polarity, miss? Do we need to flip polarity? Because they did give us a negative portion of the graph. To that, I then say, let's stare at the graph a bit first. So in this case, the current reversed from positive 2.8 to negative 2.8. In the pink color case, the current reversed from negative 2.8 go up to positive 2.8. So the direction of change is different. Okay, in fact, you can look at the graph. One is decreasing, one looks like it's increasing. Or the gradient, one is negative and one is positive. So if you really stick by the whole induced EMF is equal to negative the flux dt. Okay, so we know the polarity will be different. Let me zoom up a bit and write here for you. The induced EMF is equal to negative the flux dt. However, flux is equal to NBA. In this case, the number of turn is constant, A is constant, flux is proportional to B. If flux is proportional to B, but also B is proportional to I, means how you know the equation here, B is proportional to I. This one. If B is proportional to I, then what will happen is I have the graph, right? So from here, it's like a Russian doll. I is inside B. B is inside flux. Flux is equal to E. So from here, I can say E is proportional to negative di dt. Proportional only, all the constant can throw out one. Okay, so meaning it is proportional to this gradient. So here you have negative gradient for the blue portion. So this one you will have positive value and it will be positive 4. Load. There we go. Wow, miss, your computer listen to your command. Not always, only when it's on camera. Okay, so you make sure you draw 4. Okay, I'll zoom in for you. This part is a little bit tricky because we need this value to be at 0.3. So if I have a ruler, I will make sure I draw a dotted line cleanly slicing through the center. Okay, and this one is 0.6. And then for the next portion, we will flip it. So it will be negative 2 all the way home to 1.6. And I guess if you want to, you can draw this dotted line to indicate the time frame. Okay, so there are two ways to look at it. You can do it the equation way, where you say, hey, we double the time, so we should halve the EMF. And since we are looking at gradient, one will decrease, one will increase. That's the second way. We look at this relationship. Or you could just see it as simple as, the current went from positive to negative and negative to positive. So if the type of change that it is undergoing is reversed, one is from positive to negative, the other one is negative to positive. To oppose that change, your induced EMF have to change polarity. So CIE, they are not so hell-bent. You don't really have to draw positive then negative like what I did, because I'm trying to follow the Faraday's convention. Okay, so as long as there's a change in this gradient, positive negative gradient. So negative di dt will be positive value. Here is positive gradient. So positive di dt will be negative value. Okay, to ease your brain, I will also highlight the relevant area lah. This will be here, and then this one will be here. All right, so this graph is all in all 4 marks, but you may be wondering, wow, where are the marks? Well, if you do a lot of past year question, you can roughly guess already. 1 mark. EMF equal to 0 at your t is between 0 to 0.3 second. T is between 0.6 to 1.0 second. T is also between 1.6 second to 2.0 second. All this is the first mark. So that means you mark the zeros at the right place. Okay, all the yellow highlights. Second mark. Second mark is for the actual 4 millivolt. 4 millivolt, or E is equal to 4 millivolt at your T is between 0.3, equal to 0.6 second. Okay, one more mark. E is equal to 2 millivolt at 1.0 second to 1.6 second. Okay, and the final mark is the reverse polarity. I'm not sure when or if they will make the mark scheme a bit tighter and request that you do positive than negative. But if they do, you will have already watched this video and understood, thanks to this negative in the negative the flux dt, this blue part, negative gradient, will get positive value because negative gradient is positive value. This part here is positive gradient. Negative positive gradient will get a negative value. Okay, take some time to brain this calculus a bit if you need to. Or basically what we are drawing is the gradient function. Gradient function with a negative in front. That is EMF. But why is it a gradient function? I've already explained here. Okay, so like a Russian doll, this proportionality relationship will lead to E is proportional to di dt. Means that you can draw this graph. Alright, so that's it for this question. I think this is a lot more easier to the brain than the explained one, normally for candidates. But take it slow and easy. Always ask yourself, did the current change? If the current change, there will be no... If the current don't change, my bad, there will be no EMF, which is beautiful. You can get 1 mark already. Second question would be, if it changed by how much? Always be sensitive to the values because it sometimes can be related to your previous calculation. And last but not least, think about the polarity and the relative magnitude. The faster the change, the smaller the EMF induced. Because it's directly proportional to rate of change. When you change something slowly, the opposition, the induced EMF will be less. Isn't that normal? If we change things slowly, we can get used to it. Rule of nature, guys. Okay, so that's it for this example. If you find this video helpful, like and subscribe. Do share these videos with your friends so we can all learn physics together and ace our A2. I wish you all the best in your studies and I will see you in the next one. Goodbye now.